Okay, this is section 3, the last section for chapter 20 on electrochemistry. This section is on electrolytic cells. Some oxidation reduction reactions do not occur spontaneously, but can be driven by electrical energy. If electrical energy is required to produce a redox reaction and bring about a chemical change, an whatever. If you need to force the redox reaction to happen using electrical energy, that is an electrolytic cell. Most commercial uses of redox reactions make use of electrolytic cells. So I want to bring your attention to how this compares to voltaic cells. Voltaic cells utilize spontaneous redox reactions to change chemical energy into electrical energy. That's why we use batteries. Inside the battery, you have stored chemical energy, and as soon as you close the circuit in your device, then the redox reaction is spontaneous. It releases electrons and creates electrical energy. Electrolytic cells are the opposite of that. You need to force the redox reactions to occur because they're non-spontaneous, which means you use electrical energy to create chemical energy. So here is a side-by-side comparison, and it's not figure 13, it's figure 3.1, so I might as well just change that now. 3.1. I don't really know where the 3 comes from, but anyway. Oh, because it's section 3, figure 1. Oh, I'm such a genius. Anyway, you have a voltaic cell on the left, electrolytic cell on the right. Your electrodes are exactly the same for both, but there are distinct differences. So voltaic cell here, electrolytic cell here. The first difference I want you to notice is that the anode and the cathode have swapped. Because remember, the anode is where oxidation occurs, the cathode is where reduction occurs, and we are in a voltaic cell, we're dealing with spontaneous reactions, and electrolytic cells, we're dealing with non-spontaneous reactions. We're literally forcing it to go in the other direction. So for the voltaic cell, the zinc is oxidized, it releases electrons, and electrons then go to reduce the copper ions in the copper sulfate solution. In the electrolytic cell, we are forcing the copper to be reduced. We're forcing the copper to be oxidized. That's why it's the anode, and the electrons are released, and they're going to reduce the zinc in solution on the cathode side. And so that's why energy is required. And it's also why you see this symbol here. Hopefully you've studied electricity in physics, so you know what that symbol means, and it basically means that there is some kind of power or electrical supply that's attached there. Okay. The electrode of a cell connected to the negative terminal of a battery gets an excess of electrons and becomes the cathode of an electrolytic cell. The electrode of a cell connected to the positive terminal of a battery loses electrons to the battery and becomes the anode. So that's just a long-winded, complicated way of saying that the anode and the cathode are swapped between a battery, a voltaic cell, and an electrolytic cell. Electrons that are pumped simultaneously supply electrons to the cathode and recovered from the anode. This energy input from the battery drives the electrode reactions in the electrolytic cell. So again, the voltaic cell has a copper cathode and a zinc anode. If a battery is connected to the positive terminal, contacts the copper electrode, and the negative terminal contacts the zinc electrode, the electrons flow in opposite directions. So basically what that means is that if you attach a battery to the voltaic cell, you actually then create an electrolytic cell, and you use the energy from the battery to drive the non-spontaneous reverse reaction of oxidizing the copper and reducing the zinc. So I just said that, and we know that they swap. So the half reaction at the anode, where copper is oxidized, That's just the oxidation of copper. The half reaction at the cathode, where zinc is reduced, is the zinc ion that's in the zinc sulfate solution will gain the 2 electrons that are lost from the copper strip and will form solid zinc. So to review the major differences between voltaic and electrolytic cell. Number one, the anode and cathode of an electrolytic cell are connected to a battery or other DC source, whereas a voltaic cell serves as a source of electrical energy. Number two, electrolytic cells have electrical energy from external sources creating non-spontaneous redox reactions. Voltaic cells have spontaneous redox reactions occurring. And three, electrolytic cells have electrical energy converted to chemical energy. Voltaic cells are the opposite. Chemical energy is converted to electrical energy. So some practical real life applications of electrolytic cells, because again, one of the things that I try to do when I can is explain why the hell we give a crap about this topic. So metals like copper, silver, and gold are difficult to oxidize. It's one of the reasons why they're so expensive, is because you find them pure in nature. Maybe copper is probably the most likely of these three to be oxidized. But silver and gold, obviously we dig for them in the ground and they're expensive because they don't oxidize, they don't react. In an electrolytic cell, these metals form ions at the anode that are easily reduced at a cathode. So if you force these metals that don't like to be oxidized, you can force them to be oxidized at the anode. Then at the cathode, they're going to be more than happy to be reduced because they don't like to be oxidized, which means if they're oxidized, they're going to they're going to be very easily reduced at the cathode. This allows a solid metal from one electrode to be deposited on the other electrode, and this is called electroplating, an electrolytic process in which a metal ion is reduced and a solid metal is deposited on a surface. So this is an example of an electroplating cell. So the cell is going to have a solution of a salt of the plating metal. In this example, we're going to plate silver on top of a fork. So the object to be plated is the cathode, because remember the metal that doesn't like to be oxidized is going to be forced to be oxidized so that the ions will be deposited on the cathode where the metal ions are reduced. So the piece of plating metal is the anode. So in this example, we have the silver strip here at the anode, and we have our crappy ass, let's call it aluminum fork, that we're going to use as the cathode so that the silver from the silver metal is oxidized. So on this side, we have silver is forming the silver ion plus an electron. We're forcing it to be oxidized. The electrons are going to travel to the fork. And then because it's in a solution of silver nitrate, on this side you have silver ions. So the silver ions are going to be reduced on this side. And that's why we have the fork there, because we want to plate the fork in silver. So the silver plating cell has a solution of soluble silver salt and a silver anode. The cathode, like I said, is the object to be plated. The silver anode is connected to the positive electrode of the battery or other source of DC current. The object to be plated is connected to the negative electrode. The silver ions are reduced at the cathode according to that equation, which I wrote on the previous slide. And the silver ions are deposited as metallic silver when electrons flow through the circuit. In exchange, at the anode, metallic silver is removed as ions. So you have silver ions going into solution, and that is the half reaction for that. So this maintains the silver ion concentration of the solution, because on the left side, you have silver being deposited on top of the fork, which means in the solution down here, you're losing silver ions. That has to be balanced by the formation of silver ions, which occurs at the anode. So what would be the overall point of this is, well, you can form a thin layer of an expensive precious metal like gold or silver on top of a cheaper metal. And that's where we get silver plated objects and gold plated objects, because making something out of pure silver or pure gold is expensive. And also pure gold is quite soft. You can almost quite literally just scratch gold with like a rough kind of surface. I don't know if your fingernail would do it, but certainly rocks or some other kind of rough surface would scratch that. And so we end up with like 12, 14, 16, 18, 24 karat gold. So 24 karat gold is pure gold. It's really soft. So it's really stupid to make jewelry out of 24 karat gold, because who wants to have scratched up gold jewelry, especially when you're paying a lot of money for that? So what they do is they mix in silver with the gold, and silver is a harder metal. And so then you harden your gold. It still looks like gold, but you are basically making it harder. So then that's when you, I guess, like dilute the purity of the gold. And that's when you get like 18 karat and 14, 16, whatever carat. Okay, so that is electrolytic, oops, Bluetooth error. Real problems with it today. I don't know why, but anyway. So that is, we have electroplating as one practical application of electrolytic cells. Okay, there we go. The second application of electrolytic cells are in rechargeable cells. And this is going to be how we use both voltaic and electrolytic all at one time. So the rechargeable cell combines the redox chemistry of both of these types of electrochemical cells. When the cell converts chemical energy to electrical energy, it is a voltaic cell. That is if you use just the batteries. But when you have used up all of the chemical energy inside the voltaic cell, you then plug it in to your charger and you plug it into the wall. You use the electricity to fill up the batteries with chemical energy again. And what did I say about electrical energy being converted into chemical energy? That's an electrolytic cell. So when you are recharging the batteries, it is operating as an electrolytic cell. This standard 12-volt car battery is a set of 6 rechargeable cells. The anode in each cell is lead that is submerged in a solution of sulfuric acid. So you can see here's a sulfuric acid, and you've got the spongy lead, which is submerged, and that's why you've got your hydrogens and your sulfate. So this is one of the 6 cells in your car battery. You notice that it's 2 volts. So if you have 6 of them, that's 12 volts. So the anode half reaction is lead reacting with the sulfate ions to form lead sulfate. So in this example, lead goes from 0 to +2. That is oxidation. Oxidation is at the anode. Okay. Notice that the anode is the positive end of the terminal. Electrons move through the circuit to the cathode, where lead oxide is reduced as follows. So we have lead oxide, and it combines with the hydrogen, the sulfate, and the electrons to form lead sulfate and water. So again, here, lead is +4, and here is +2, that is reduction. The next redox reaction for the discharge cycle is as follows. So that this is how the the energy is discharged from the battery. You have the lead plus the lead oxide plus the sulfuric acid forming the lead sulfate plus the water. That's the whole redox reaction together. A car's battery produces the electrical energy that's needed to start the engine. That's pretty much all the battery is there for, to start the engine. The sulfuric acid, which is present as ions, of course, is consumed, and lead sulfate builds up as a white powder on the electrodes. Once the car is running, however, the half reactions are reversed by voltage produced by a component in the car called the alternator. So lead oxide, and sulfuric acid are regenerated. The battery can be recharged as long as all of the reactants are present and all of the reactions are reversible. Once you have here, the lead sulfate, when you have that white powder building up on the electrodes, if you have that building up on the electrodes, that means that the lead sulfate is being taken out of that electrolytic cell, and after a while you don't have enough reactants left to keep the process going. So the car battery produces the energy that's needed to start the engine. That's why if you leave the car lights on overnight, it drains the battery, because once the engine is started, then you go to combustion when you're burning the gasoline, and then that energy is used to recharge the battery. That's like if you have a dead battery and you can connect it to another running car, and you can use the energy from that running car to jumpstart your battery just enough to get the engine started. And then once you get it started, you drive it around for a little bit because you want to have the car running on combustion to recharge that battery. The end.